Thank you for stopping by. My name is Ming, and this is a special Encore presentation for a talk that I gave at ASMS just a few weeks ago in Philadelphia. And so what I want to talk to you today about is the mass spectrometry query language. And we hope that it's a flexible way to discover, explore, and extract mass spectrometry data. And so to get started, I want to tell you a little bit of the story. And so I work in Peter Dorstein's lab, and I'm just minding my own business most of the time. And sometimes Peter has the gall to come in and ask me questions. And so some of the things he asks are very reasonable, but they're very simple, but they are complicated to answer. So for one example, he might come in and say, can we find all brominated compounds, all glycans, all siderophores, all carnitines, all bile acids, and all public mass spectrometry data available at GMPS? And at the surface, it seems very simple, but even though we're good friends, I don't have the time or the resources to actually answer these questions effectively. And so because there's a clear need to find these answers, I asked the question to myself, can I develop a universal computational solution that helps answer these at scale and is flexible enough for chemists to do it themselves? And so we think we have one answer to this. I think we're on our way to solving this problem. And I want to tell you a little bit about the mass spectrometry query language and the pillars that support it, and hopefully what can at least move the needle a little bit. And so one of the pillars for the MassQL query language is that it's understandable. And so we want to empower mass spectrometrists and chemists themselves to be able to read and write this particular language. Next, it needs to be flexible. So we want it to be able to capture a wide variety of mass spectrometry patterns that can exist so that you can easily find what you're looking for. Third is we want this to be scalable. And so not only to be able to look at one single spectrum to a whole file to an entire project, but also scale up to entire repositories. And finally, we want this to be reusable. And if you take a lot of effort to figure out, given your own domain knowledge in your head, what you're looking for, what kinds of fragmentation, what kinds of isotopic patterns that you're actually looking for, we hope that you're able to communicate these ideas as in a real language with others so that they can reuse that knowledge that you've essentially codified, as well as just simply communicating ideas. And so going through these, I want to just take these step by step and show you how we've made these things real. In this understandable aspect, we're going to walk you through the most simple query possible. And so just kind of as a construction, we've also translated this to English and other languages, for example, here Portuguese, and we apologize if the translation isn't perfect. But for this particular example, this very first part about the query, it says, I want MS2 data. And you can see color-coded the translations into these natural languages. And then another thing we might want to do is look for MS2 spectra that have a particular peak, in this example, a 468 M over Z peak. And we can see that it's translated back into these natural languages to be better understood. And then finally, what if we want to add another condition? We want to say, let's look for this other peak at 660 M over Z. And it's simple as tacking these conditions on into the query to be a flexible expression. In order to make this even more natural for mass spectrometrists, we have also created a visualizer that is a little bit more natural to see. And so if you have a particular query, we'll render it as a pseudo spectrum showing the bounds of which masses you're looking for, the M over Z tolerances, the intensity tolerances, expected intensities, if those are the options you choose. And number two, it also allows us to overlay real spectra on top of the query so you can explain exactly why this real spectrum was found by the query language. And so moving on for flexibility, I want to describe to you a subset of the functionality of the language and the complex patterns that you can actually describe. And so in this very simple example, working with Daniel Petrus, he's looking for this family of molecules called albicidins with these two distinctive large peaks. And so he simply can ask, I want to look for mass 468 and 660 in the MSMS, find me all of them in my data set and pull them out. And so that's querying the MS2. And now we can also query across MS1. Certain types of molecules you might be interested in will have distinctive isotopic patterns. And working with Allegra Aaron at UC San Diego, she's interested in siderophores. And with iron-bound molecules, there's a distinctive isotopic pattern for the iron itself. And so she was able to formulate a query and start looking for iron siderophores by looking at distinctive isotopic patterns that she could define herself. And then we're able to combine both of these queries. We can say, look for distinctive isotope patterns in the MS1 and a characteristic fragmentation in the MS2 if that's something you're looking for, as well as add in mass spectrometry adjacent features. So for example, here using retention time, if there's a particular bounds that you care about, as well as looking for regions of ion mobility that a lot of modern mass spectrometers might have. And moving on to this third pillar of scalability, we want to be able to go up to billions of spectra in entire repositories. And so just one example, working with Nina Zhao from the University of Washington, she specifically cares about organophosphate esters in the environment. And so these organophosphate esters, they're used in flame retardants, they make their way into the environment, so it's an ecological concern. And so there's a huge diversity of these organophosphate esters, but something that's particularly unique to these set of compounds is there's a 98.98 m/z fragment that is universal to all of them. And so working with Nina, we were able to formulate the simple query to look for that particular salient peak. And with that, what we were able to do is look through all public GMPS data using MassQL, and this is about 1.1 billion MSMS public data, which is nearly impossible to manually look through. And we were able to filter this down onto 330,000 MSMS spectra that had this particular peak as the dominant peak in the spectrum. But this still is pretty hard to go through and kind of sort through what's going on. And so the very first technique we used to reduce this by a couple orders of magnitude again after MassQL was merging identical MSMS spectra together into consensus spectra. Broadly, this is known as MSMS clustering, and the particular tool that we used was called Falcon, and this allowed us to reduce it from 338,000 down to 2,700 unique MSMS spectra. So 2 orders of magnitude, not so bad, but still a lot of data to look through. And one of the final tools we used to organize and visualize this data enabled us to group similar molecules that have similar fragmentation together in a nice network, and we call this approach molecular networking that was available at GMPS. And this further enabled us to reduce it another order of magnitude into about 169 families of related compounds based upon the similarity in their MSMS spectra. And so from this, Nina was able to mine a particular MSMS network that I'm showing here up on screen. And what was unique about her mining is that she was able to find new organophosphate esters that were previously unidentified. And what was really cool is not only was she able to identify new ones from all this public data, but some of the organophosphate esters that she found that were new were in her own data that she had published previously. And the fact that she had already spent so much time digging through this data and didn't find these, and with MassQL was able to find these now, it exemplifies both the power of MassQL for analyzing your own data, but also the fact that she found new ones, it expands this pool that you can start prioritizing and searching through. And so finally, I want to get to the point of reusability. And so how can we start sharing and reusing queries across a community? And so kind of our first steps in this direction to make this really possible is we wanted to create a software ecosystem so that it can be pervasive. It can be really thrown out into the community. And so one of the things that we've made is a Python version of MassQL that you can run on the command line. You can integrate into software. There's also an R version working with Johannes Reiner. And both of these are open source that you can use today. Additionally, we also want to meet people where they are. And so working with people within the community, we've integrated it into open source software such as MZMine with Robin Schmidt and Unideck with Michael Marty, as well as we've incorporated it into GMPS as workflows that the whole community can run. as well as interactive dashboards that you can even try out today. And so once we start getting MassQL out there, the dream is that you can get queries from anywhere. You can come up with it in your own head. You can ask others in the community. Maybe your lab mate wrote a query. You can read it, hopefully, from publications whenever they publish their methods. And we're building a compendium of queries that the community has created. And so any of these sources you can grab queries from for substructures that you want to look for. And once you have that, you can go and apply it to your data, whatever software that you use. So for example, if it's Python or R that you're more comfortable with, if it's MZMine, you can just simply copy and paste and apply it to your data already in an ecosystem that you're working with. And so if you are a tool developer or you're a commercial entity and you want to integrate this into your own software, reach out to us. We would love to help and work together. And so circling back upon what we talked about at the beginning of this presentation, one particular compound class that Peter and the whole lab was interested in over the last couple of weeks on the Slack channel was carnitines. And whenever Peter asked me about carnitines, since we invented MassQL, you know what I could tell him? Do it yourself. Do it yourself. And so he was able to write his own query for these particular distinctive fragments for carnitines and search public mass spectrometry data for them. And again, we were able to reduce it from 1.1 billion MSMS down to about 2 million MSMS matches and about 50,000 unique MSMS spectra in 6,000 families. So definitely a lot to mine, but at least it gives people the power to ask these questions flexibly themselves. And so the final takeaway I want to have from this presentation is that MassQL, we hope that it empowers chemists and mass spectrometrists that might not be experts in software development and scalable systems to be able to ask these kinds of questions at scale in a super flexible way. And also, we hope that MassQL, just because we've made it a vibrant software ecosystem that enables bioinformaticians to integrate into their own software to give them the flexibility to also query for patterns that they might want to look for as well. And then finally, building upon all of this, once we have a software ecosystem integrated into bioinformatics software for the community, we hope that it's universally reusable in a way that a real language is. Simply copy and pasting a query that you've written and sharing with the rest of the community and others can apply it seamlessly, that's kind of the dream. And so none of this would have been possible without all the support at UCSD and collaborators from around the world. So Peter's lab, my PhD lab, Nuno Bandeira, the GARG lab at Georgia Tech, Alan Jarmusch at the NIH, the Petrus lab at Tübingen, and the Sanchez lab at UC Santa Cruz. And there's so many others I want to thank as well, the whole metabolomics mass spectrometry community. And definitely reach out if you want to use it, you want to integrate it, or if you have ideas to collaborate. Thank you so much. Okay, MassQL, take one. Welcome. Thank you for stopping. MassQL, take two. Welcome. Thanks for staying. Damn it. MassQL, take three.